Welcome to the first of several videos on the shell method for determining volume. This video will only show rotation about the y-axis. There'll be other videos that show rotation about other axes. So we've already talked about how to determine the volume of a solid using the disk and washer method. Let's take a look at an animation to develop the idea of how we're going to use cylindrical shells to determine the volume of a solid. So if we considered this shaded region here rotated about the y-axis, we know by now that it would produce a solid. But if we take a look at just the solid created by rotating these very thin red rectangles about the y-axis, it would produce something called a cylindrical shell, as we see here in red. And the idea behind the shell method is, as we increase the number of shells, the volume will approach the volume of the region rotated about the y-axis, as we see here. Now if we go back and take a look at just one of the shells, we have to ask ourselves, how would we find the volume of just one shell? Well, we'd have to find the surface area of the shell and then multiply it by its thickness. So let's take a closer look at just one shell. If we wanted to rotate the region bounded by the x and y axis and this blue function, we know it would produce a solid that looks something like this. And this very thin, hollow cylinder would represent one shell that we could use to determine that volume. One thing we should be able to recognize is if we cut this cylindrical shell and stretch it out, it would be a long rectangle. And this distance here would come from the circumference of this circle, which is equal to 2 pi r, and this distance here would be the height. So the surface area of the cylindrical shell, would be equal to 2 pi r times h. And then to determine the volume of the shell, we'd have to multiply by its thickness. Well, the thickness of this shell would be the thickness of this very thin rectangle that was used to create the shell as it rotated about the y-axis. And this width would be equal to delta x. So to find the volume of the shell, we have the volume equal to 2 pi r h times the width, and all of this will be equal to 2 pi times what we'll call r of x, the radius function, times h of x, the height function, and the width will be delta x. So the volume of the solid would be equal to the sum of the volumes of the shells as the number of shells approach infinity. So to formalize this, using the shell method with a vertical axis of rotation, the volume will be equal to this definite integral, where r of x is the radius, h of x would be the height, and the limits of integration a and b are the interval on the x-axis. In order to set this up, it's important to sketch a representative rectangle just like we did in the washer method. However, for the shell method, the representative rectangle will be parallel to the axis of rotation. So if we're rotating about the y-axis, we could use this as a representative rectangle. And the width of this rectangle would be the width of the shell, and this would be delta x, and that's a reminder that we'll integrate with respect to x. R of x would be the distance between the axis of revolution and the center of the rectangle. So this would be our r of x. And then h of x is the height of the rectangle, and that would be this distance here. And then lastly, we integrate from a to b, where a and b is the interval along the x-axis. So this would be a, and this would be b. And just to emphasize this one more time, let's go ahead and take a look at one more animation. Again, if we wanted to use the method of cylindrical shells to determine the volume, so to find the volume using shells, we'd start with one shell and then start accumulating the volume of the individual shells. And as the number of shells approached infinity, we would approach the volume of the actual solid. Okay, let's go ahead and look at an example. We want to use the shell method to determine the area bounded by the region rotated about the y-axis. So since we're rotating about the y-axis, we will sketch a rectangle that would represent one shell, and since we're rotating about the y-axis, Our representative rectangle will be parallel to the y-axis, so it might look something like this. The width of this rectangle is delta x, which tells us we'll integrate with respect to x, as we see here. So let's go ahead and see if we can set this up. We have the volume is equal to 2 pi. Since we're integrating with respect to x, we know that a would be 0 and b would be 2 along the x-axis. Next, we want the radius function. Well, the radius function would be the distance from the axis of rotation to the center of the rectangle. That would be that distance here. And this distance would just be x times the height of the rectangle. Well, the height would be the distance between the function and the x-axis. And this would be equal to y, and y is equal to x squared plus 2. And then we're integrating with respect to x. Let's go ahead and distribute the x. So looks like we'll have x cubed plus 2x. Now we'll go ahead and find the antiderivative. So we'll have x to the fourth over 4 plus 2 times x squared over 2. I'm going to go ahead and rewrite this as 1/4 x to the fourth plus x squared. Now we'll go ahead and evaluate this at the upper and lower limits of integration. So first we'll replace x with 2. Then when we replace x with 0, both terms would be 0. So we have 2 pi times, this is going to be 4 plus 4, that would be 8. So this volume is going to be equal to 16 pi cubic units. Okay, that'll do it for this first video. Next we'll take a look at rotating about the x-axis using the shell method. Hope you found this helpful.